today to be here facilitating these discussions. I've had the honor to know several of these gentlemen for 20+ years. In particular, Keith Belvin. I've known Keith since 1988 when he hired my advisor as a grantee, and I was fortunate enough to tag along and worked with Keith in the same office for a while. Suresh, Josh, and I have been colleagues for 20+ years as well, and I've also had the pleasure of working with Carlos and John Dorsey, and I've met Dan Masnick on a couple of occasions, so it's my honor to be here. We will be discussing the presentations today, and we have a microphone that we're going to pass around, so please feel free to contribute. The microphone will be directed to you. I will try my best to repeat your question to the panel and elicit some discussion. So please feel free to jump in, ask any questions, put out any possible solutions you may have to this problem, and I guess with that, open the floor to you guys to go ahead and ask some questions. All right, Carrie.
So I guess this is to John. When I like the tendon-operated structure, it looks like, so you've got in the direction of the tendons, you know, that truss is very small, and then in the 90-degree axis, if you will, that truss is actually bigger because it's taking up any side loads. So it looks like by intent, the only loads that would be on those side loads would be spurious dynamic loads. If everything went perfect, there really wouldn't be anything there. However, for instance, the grappling idea, where you grapple it and then the spacecraft is attached to the object and you've grabbed it and then you start to de-spin, is clearly going to put side loads on it. So I'm assuming you haven't really gone to the trouble to size it so much lately, but you must have thought about it. And
well, yeah, you're right. It's hard to get sizing loads
right
out of high-level studies, but you know, as a first thought, that's, you know, 3 fingers. When I grab something, the idea is to grab a hold of it with 3 fingers so that I wouldn't want to do this and bend my finger sideways and break it, right? But if I grab something with 3 fingers, then that gives me a better load distribution in the manipulator. So one of the areas of research, right now we've been mostly developing the manipulator itself and trying to get the motion and the controls working, the mechanical systems. We haven't really gotten into the operations yet, but obviously, just like any crane manipulator system, you have to come up with the ConOps to go along with the mission. And that would be part of, yeah, you want to definitely avoid major side loads if it's just a single manipulator.
Any other questions? A follow-up to that, perhaps? One other question I had on the talisman concept is, of course, it's extremely large, lightweight. So one of the obvious questions becomes, how flexible is this system, and how do you guys intend to manage the flexibility of that system, the structural dynamics, essentially?
Once you get design requirements, you know, we have some freedom. The truss that we've sized was solely based on the shuttle arm. The shuttle arm has a criteria of fully extended out at 50 feet. If you put like a 15-pound tip load on it, it has a deflection requirement. So we basically sized our system for that load. So it's quote unquote shuttle-like in its performance. But you're right. If you need to increase stiffness, since it's a tension stiffened structure, you can do that by adjusting the tendons, larger area. Different materials is one way to do it. You can also work with the truss. The spreader height actually influences the stiffness of the system. So once you get a good set of requirements, then we have to really go in and do the real design work to size a system. So what you see is representative. We have a lot of kind of design factors at our disposal, so when we do get a real set of mission requirements, that we could try to see if we could design the system or not.
Great, thank you. Yes, Jill.
So Can you hear me okay? There it is, okay. So I apologize because I missed the first couple of talks, but what I'm curious about is for each of the facets of the problem that you guys talked about, what is the thing that's sort of keeping you up at night about that facet of the problem, either about your candidate solution that you're looking into or about the way you're thinking about the problem? And then for everybody else, what in your discipline area could help with that thing that that person's thinking about? Or for you, what did you hear in the other people's talks that maybe is a thread to pull on that could help address that?
So I guess essentially Jill's asking, what are some of the biggest challenges as you see right now, and how do we manage this in, I guess, a cross-directorate way to work together to best solve these problems? Is that a fair assessment? Thank you. I guess that's pretty much open to anyone on the panel here.
I thought everybody had an answer.
We did mention some of the challenges that we have to wrestle with, and I don't know at what point you walked in. The difficulties in nailing down physical parameters of the asteroids or the boulders. So that's one of the things that we have to grapple with in dynamics and control.
Yeah, and I have something to add to that, namely, Carlos also had it on his slide. We need to develop methods for optimal, robust, and adaptive control in the pre-capture, mid-capture, and post-capture stages for stabilization, and that have to be tolerant to flexible modes as well as uncertainties and time variations and non-linearities. And in addition, we don't know much about the asteroids, so we need system ID techniques, which our branch has expertise in it, to identify the mass inertia properties of the uncooperating, non-cooperative object. So that's where I think we could collaborate with your group there to study that. And also flexibility in John Dorsey's system. I think we need to address how to design robust controllers which will account for that. And I think, but my thinking was that this will have better stiffness than just flexible arms because of the cable stiffening. And like you said, you can increase the stiffness by adjusting the cable tension. And also, I didn't. One thing I learned from your talk is that the joints are very heavy. I had not realized that, and the joints is the heaviest part of the
in the conventional manipulator. Yeah, they are very heavy.
Because it makes it a very attractive concept. I think.
I would like to take Jill's question and point it directly to Dan Masnick. In particular, in your presentation, and I think Jill may have missed this, Dan was talking about three fundamental elements: the identify, redirect, and explore. Of those three, based on my background, I kind of focus right on the redirect portion of that mission because that's where my experience is. But of those three, which do you consider to be the most difficult?
Well, I think Carlos hit upon it, and Suresh hit upon it as well. Characterization is a key, right? When you want to do something, you need to know what you're doing it on. Satellites, you know, we have specs, we have drawings, we have mass, and as Keith talked about, sometimes it's cooperative, sometimes it's not so cooperative, and sometimes you induce rates on it that make it uncooperative. The uncertainties and properties are a key area, and how do we do that remotely? Remote characterization for option A, if we go out and find a small asteroid, we basically got to do that all remotely. Radar is a key tool, ground-based radar, but for option B, we have the ability to have precursors. Two of the targets, I didn't have time to get into all the details, but two of the targets, Bennu and 1999 JU3, and actually three, Itokawa we've already been to. Bennu and JU3, we have precursors planned right now, OSIRIS-REx to Bennu and Hayabusa 2. So that's a critical function. You think about going to the moon. We put humans down on the surface of the moon, and we had dozens of probes characterizing, provided that precursor information. And somehow we've kind of lost that aspect in the modern age. It's kind of like, oh, let's just go out there and go to an asteroid, or send humans to an asteroid without that characterization. The other huge part, and if there's one aspect, and it's both for option A and option B, but probably option B is a little bit more more of a risk or more of an issue, and that's the autonomous operations. We think of robotic systems in terrestrial standpoints. We can teleoperate things. We've got a controller. There's going to be a time delay. All these operations have to be done in a sequenced manner, and they have to be able to adapt to uncertainties ranging from minor stuff, adjust and keep doing the operation, to, oh my gosh, we got to get out of here. And that's a big issue. Autonomous operations and terrain relative navigation for option B is something that we're working on as an agency, but it's going to take on new dimensions for the asteroid if we go pick up a boulder off the surface of a large asteroid.
So for the for the manipulator technology, we just as of about a week and a half ago, MDA under contract, we had them under contract, delivered the control system for a single arm. And what we don't have is when you have multi-arm. So how do you control multi-arms working together? What are the optimum poses for these multiple arms to grab, say, an object, to minimize the loads on each arm? There's a whole how do you take 2, 3, 4 arms or whatever and make them work together to make a system and optimize that system? So that's a big thing that, I'd love to see somebody from Lang. Yeah, got volunteers, great, come on. We're gonna have 2 arms sitting over in the...
Can we possibly formulate what you just said into an optimal control problem? I'm sure.
I'm not a controls person, so I don't know if you can.
I was just kind of throwing that out there.
I'm sorry, can I get that question again? Yes, if you could formulate this as an optimal control problem.
Yeah,
is that your question?
What John just described.
Oh, okay.
You can always formulate problems. Mathematically it's possible, but solving it sometimes has become very difficult.
So do you guys look at all, I don't know if you're done, but do you look at all at, there's some ROV, the underwater, undersea ROV manipulator technologies where they use multiple arms. They have people who are controlling them, but they do a lot of work that involves really precise.
A lot of that's teleoperated, right?
Right.
They're just sitting there doing
But I would assume that, I was just throwing that out there as something that maybe there have been studies in those fields that relate to what you're talking about.
Well, some work has been done. If you can go on, the web, and a lot of universities. You can see robotic hands catching balls and stuff like that, doing a lot of these operations. So I think people are working these kind of problems, but they're working on something this scale, where now I want this to be 20 meters long, and I'm grabbing how big's the boulder and what's the spin rate?
50 to
and
500
I'm trying,
tons,
and I've got to optimize the operations and the poses for this system, doing that kind of, say, grabbing that kind of payload, or it could be a satellite, for satellite type servicing. But it's just a general area that my team is 4 people, so we're all stretched really thin, and we don't really have that expertise. But if that expertise was at Langley, and somebody, we could be a test bed for somebody if they wanted to actually develop algorithms and try them out on real structures. We could be a test bed for somebody that wants to develop end effectors for different servicing or grappling or any other kind of missions. I think there's lots of possibilities. The flat floor that we have now over in 1293 is I call it a zero G simulation facility. But that just in itself would allow us to actually try operations with full-scale arms, large masses. We can float the spacecraft with the arms on it, and we can float the masses, so everything's free-floating in 2D, and we can see if we can make this stuff work or not.
Yeah, and on that same flat floor over the summer and the fall, we're going to be testing out the space frame concept for what we're calling the contact and restraint system. or the legs, as they're known, and one of those is how you restrain that object. Now, when we were looking at it on the surface with the space frame capture system, we had a very deliberate one-arm movement. It didn't show up in the animation because that was artistic. They moved all 3 arms at the same time. But it gets to what John's saying. There's complexities with that. So what we have actually is one of the arms come over, and when it makes contact, it basically stops. Now, you're in a microgravity environment. The object may move slightly, but the idea is to move deliberately and slowly, stop. The next arm comes in, stops. The third arm comes in, stops. And then when you might have to iterate, you know, if there's a slight movement, if all of a sudden the sensors say this came away a little bit, you might very slowly touch again. But then finally at the end, all 3 would work in unison in basically a final pose to capture the object. Now, that's different than the hybrid approach, which I showed you with these robotic manipulators and the microspine, because they're basically going to hold the thing while we jump off the surface. So that space frame is actually going to push off and ascend, and now that space frame has to do a similar operation off the surface, come around, grapple, 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 while the inertia properties are being refined along the way. So it's going to be an interesting orchestration or a ballet of how that's done.
So I'd like to go back to Jill's question just for a minute, bring it up a level. What I worry about is that we jump into our favorite technology. You know, I'm a controls guy. I'm going to solve this complex controls problem, and I'm going to synchronize everything. Or I'm a structural dynamist or a structures guy. I'm going to solve it that way. It's really a systems problem. Really like the approach that Dan is taking. We need to be thinking about the general architecture at first for this capture problem, and not just one, but many, because once we choose that architecture, it locks in every other issue and problem that we're going to have. And so understanding the trades there is extremely important before we jump into our favorite solution. And then, you know, thinking some radical approaches. You know, I'm thinking right now, you know, I live on the York River, and I watch ospreys catch fish. And it's really interesting to see them struggle at first when they first pick this up, because the fish is doing all this number. But after a while, either they stabilize or they kill the fish, and then they fly pretty normally. But you know what can you learn about, you know, that grappling from nature? Even, you know, some examples like that. I was talking to Dan yesterday. I know ESA's rendezvousing with a comet, and they're using a harpoon to penetrate the ice ball, you know, to land on. And we've got experience, you know, with MSL doing the sky crane as an autonomous system, landing a vehicle on the surface, which is just fantastic. I mean, it's complex. So once we get that overall architecture and working it from the systems level, I think we will find some creative solutions, and then the technologies to enable those solutions. But the other big piece is to make this thing affordable. You know, it is not a human-rated mission. If we fail, you know, should we spend 10 years of the agency's budget for one try, or should we do some things on the cheap and learn and take some risk along the way? And so our typical approaches of, you know, failure is not an option, shouldn't be applied to this mission, I don't think. I think we should try some unique things, and if you guys got creative ideas, even how to prototype it. John's talking about a flat floor, but if there are other ways to get some experimental data about the approaches, that's fantastic.
Yeah, and Keith just kind of hit on it. The asteroid redirect mission is a technology demonstration mission. Of course, it has a pretty high visibility at this point, and will continue to have that. So, and as good engineers and scientists, we want it to succeed. But we also have to have graceful degradation, and that is, and we actually in option B we have multiple fallbacks, including Regulus sampling in the contact arms. So if we're unsuccessful in capturing the boulder, we have multiple attempts at the surface at different locations, the ability to release the boulder. So, you know, failure is in the eye of the beholder sometimes. If we can accomplish, you know, obviously the goal is to bring back the boulder, But even if we don't accomplish that, we will learn a tremendous amount, and if we could successfully get the spacecraft, we don't put the spacecraft itself in danger. You've got value in the mission to the agency.
Do we have any more questions in the audience?
I had one here, and I guess this is for Carlos, but the trajectories you showed zooming into the tumbling asteroid or even a more cooperatively spinning one, those take continuous fuel all the way down, right? Continuous to maintain. Once you grapple it, can you stop using that fuel, or would that be too much tension on the effector arms?
You can stop using fuel, but afterwards you need to spend fuel to despin everything, because you want your solar arrays pointed at the sun. You don't want to keep tumbling too long, and you also eventually want to point your solar electric propulsion thrusters in the right direction to come home.
Is all the D-spin not solar electric propulsion then? It's all stored fuel?
RCS, yeah.
Yeah. Yeah, not to mention communication. You want to be able to point so you can talk to the Earth pretty quickly.
You mentioned the trade between speed and fuel used, and I thought just go very slowly, but I guess that's why you can't. You lose communication while you're tumbling and solar power.
Yeah.
This is for Carlos as well. In the third simulation that you show of general motion, I guess the motion is non-periodic. And presumably characterize that motion is much more difficult if you look into the spin only or precession and spin. I guess you will have to calculate it or estimate the 3 moments of inertia and the initial condition. Do you know how sensitive will be the predicted trajectory to good estimates of those quantities, or you haven't looked into that?
Let me answer or address periodicity. The tumbling motion of an unsymmetric rigid body is described by Jacobian elliptic integrals, and there is some periodicity in those. They're like modified sine and cosine. So if you look at the curves of the Jacobi elliptic functions, you will see some periodicity in it, actually. We haven't looked at sensitivity to uncertainties in the inertia ratios or the estimates of angular velocity, but just as you say, the poorer your knowledge of either of those, your trajectory is going to be off.
I think we have a question over here.
Yeah, I was just wondering whether or not y'all looked at all at using the charged particle beam in order to change the rotation, to slow it down a little bit, rather than having the spaceship.
Yeah. Yeah, one of the approaches that has been proposed for option A is to use the SEP thrusters and do utilize the ion beam that comes out, the plasma beam that comes out, and slow down the rotation. One of the fundamental problems is, first of all, it takes propellant to do that. It's efficient, but you also have to point it. You have to keep the spacecraft pointed, and you have uncertainties as where the center of mass is, et cetera. But that has been proposed. Whether or not JPL has not definitively shown analysis that shows that it's practical, but it is a possible solution.
Well, the other comment I was going to make is for your trying to figure out what the mass is and everything else, if you hit it with this particle beam, then you could probably figure out from the change and how it was rotating, what the mass was, maybe what the moments are. I mean, if you could pick out a spot and hit it, and you knew you hit it there, and you probably could do that by watching it with an IR camera, because you're going to get a hot spot, so you would know where you hit it, then you may be able to figure out some of your moments remotely without having to go up and actually touch the thing.
One problem with the current Hall thrusters is the beam divergence. and there's a lot of uncertainty as to how many of those particles are actually hitting it. So you've got to factor that into the calculation as well. It's not like a culminated beam that every particle coming out of these SEP thrusters hits the target. So that's just another complication, and the fact that if it's a rubble pile and you start slowing down substantially the rotation rate, it should stay together because you're getting slower. But as things shift from a equilibrium state, you might have things that you don't want to have happen. And if you haven't put the bag around it yet, then you have to deal with that situation.
Would there also be a problem with knowing whether the ions were reflected specularly or
they're absorbed?
Yeah.
Yeah.
That may be a problem. Yeah.
Yeah, I think they know the properties of the ions as they hit sufficiently to know whether they're absorptive.
And you may be able to figure that out by how much you heat up a spot.
Yeah.
So, but
can you throw a tethered mass from the spacecraft onto the asteroid and then measure the velocity and rotation?
Throw a tethered mass.
It could be a rubble pile. When you throw something at it, it could disintegrate.
Depends on the mass of that tethered object, yeah.
Wait!
Oh man, we don't know. I'm gonna bring that.
I don't think that idea has been talked about in that terms. I mean, people have talked about tethers for de-spinning and kind of a yo-yo approach. For the enhanced gravity tractor approach, one of the ideas was to put the mass on a tether, the boulder, and that way you could get it closer to the asteroid, keep it away from the spacecraft from a safety standpoint. But we haven't had time to look at that aspect. There certainly are things that tethers can bring to the table. It's just another complexity and cost into the system.
Do we have any other questions? You guys are gonna make me ask another question. Thank you.
I have a really broad question that I feel like maybe everybody thinks about but doesn't ask whenever they hear about the concept that you're going to redirect this really big asteroid potentially with the gravitational pull of your spacecraft. What I always wonder is there going to be somebody at NASA who calculates, okay, we changed the orbit of this asteroid and in 100 years is it going to come back and like crash into, or you know what I'm saying, who calculates the effect that we have? You want to have an effect on it, that's the goal.
Right.
So I've just always wondered that.
Yeah, absolutely. So there's two issues. There are what we call potentially hazardous asteroids, or PHOs, potentially hazardous objects. Those are the ones that come close proximity to the Earth. Bennu actually is classified as a PHA. It has, I think it's 140 years in the future. It has some minuscule chance of an impact. It's one of the more benign PHAs, meaning if you did perturb it in a negative way, you'd have plenty of time to deal with it. The other aspect is you can go to a hazardous size object that has no chance of hitting the Earth. So you can take that approach. You can also take the approach that if you did have a situation like Bennu and we do it properly, which we should be able to do, we can make it less of a hazard. We can even eliminate that minuscule chance 100 or 200 years in the future that's a threat. And that's a beautiful demonstration of exactly what we need to do. So certainly it's a concern that the public, especially even bringing back an asteroid to cislunar space. A lot of people are like, whoa, hang on a second. You've been trying to keep these things away from us. And sometimes you have to do things, or you can do things that you can learn from in a safe manner that can help you when you do need to take action. But yes, we have been thinking about that very, very much.
Just to add on to that, I know we kind of went through it on walkthrough, but can you guys go over some of the numbers just along the lines of, if we do affect an asteroid? I know you mentioned something like it would take 6 months for us to see if we move the orbit minuscule amount or something like that.
She was asking the gravity tractor. I said it takes about 3 months to do the gravity tractoring for you to get a measurable deflection of orbit.
Yeah, somewhere between 60 to 90 days. Again, it depends on the target that you go to. But the way that we're measuring the orbit, first of all, we have a spacecraft there, so we use the Deep Space Network to communicate with the spacecraft. So we know its location in the solar system very accurately. And then the spacecraft itself uses some instrumentation, whether it's LiDAR or just optical cameras, to figure out its distance from the asteroid. And with those combination of things, you can figure out what the orbit is before you do the planetary defense demonstration. And that can either be a gravity tractor, or we could do like a kinetic impactor where you actually run in at high speed with another spacecraft, observe it. The key thing is that you have to have the right orbital alignment between the Earth, the Deep Space Network, and the asteroid. So even though we may just do the gravity tractor for, say, 2 months, we may have to wait, depending on the particular specifics of the orbits, up to maybe, you know, another 3 to 6 months to wait for the right time to measure it. And of course, that also depends on how much you move it. The more you move it, the less accurately you need to know to say, yes, we made a discernible change.
Kerry?
Yeah. And these delta V's were what?
These delta V's.
Oh, for the asteroid, you know, the delta V.
Yeah. So for a real deflection effort, and without getting too much into the gory details, basically, the more time, the better. Okay. If you're trying to deflect something from hitting the Earth, you know, you're basically trying to change its position in space so that it doesn't, it's not in the same position as the Earth, you know, at the wrong time. So you're trying to make it arrive earlier or later, just like a car passing a train track, right? You don't want to be there when the train's there. So either you speed up or you slow down the car. And that's what we're doing with this asteroid, either for a real defense or a demonstration. For a real defense, if you have like 10 years of warning time, typically about 1 centimeter per second of delta V, maybe a couple centimeters per second is needed. Sounds like a very small amount, and it is, but you remember you've got a very big mass potentially that you're applying it to, so you still have to have a lot of force, a lot of momentum. For the demonstration, we're talking about a fraction of a millimeter per second, say 1/10 of a millimeter per second, to produce a discernible effect. And that's kind of at the measurement threshold of our instrumentation accuracy, how well we can measure the position.
I have a question on the orbital propagation. So how much, so you can propagate the orbit of the asteroid after deflection in 10 years, 100 years. You can, indefinite time, right? But how much do we trust? Like, how much further can you propagate within your trust region?
I'm definitely not the expert on long-term orbit propagation, but the folks at JPL that are experts in that, for asteroids, for most conditions, they can estimate decades to hundreds of years. Okay. Now, comets or asteroids with interesting or unknown properties can change that orbit, and if you don't know those properties, which a lot of them we don't know, you can have some inaccuracies. Comets are the big one because they outgas and they create basically little thrusters on themselves that can steer them into a different orbit. But asteroids are typically quiescent unless they show some cometary activity. Yeah. But there are thermal re-emissions like the Yarkovsky effect that you heat up the asteroid, and then as it spins, just like at night concrete re-emits heat, the solar energy it acquires, that actually moves in their orbits. But they have models, and they have a lot of data that is consistent with, you know, the models are consistent with the observations that they made.
Okay, that goes to her question. Yeah, we deflected for 500 meters. In 10 years, it's not going to hit Earth, but maybe down, say, 1,000 years, it's going to come back and hit Earth.
It could.
There's a possibility because we deflected trajectory.
Yeah, there's always that possibility, but again, because we know the orbit so well, we do it the right way to actually make that even a larger miss. That's right. So yeah, if you do it the wrong way, and of course if we have to do a real one, when the chips are down and you really have to do it, yeah, you want to make sure you do it right. So better to practice beforehand, practice before you play, because it's important play.
I have a question from Jill on the back.
So I was noodling on Keith's comment about, do we design the uber robust mission, or do we, do something that's a little bit cheaper and maybe have an opportunity to, make a few goes, and coupling that with a lot of the comments that we've heard about uncertainty, all the different uncertainties related to this mission. So where are we in terms of probabilistic design methods, and how would, where does that need to be in order to, if we pursue the approach that Keith was talking about, where we maybe try, we don't go for the, 100% going to succeed approach, and instead we have to market, hey, we're trying something, a little out there, and our confidence in being able to, capture versus interrogate versus do something else to this asteroid is X. And our ability to predict what that might look like, and where are we? What do we need to be? What do we need to do there?
Fortunately, your panel moderator is an expert in some of these systems.
Thank you, Jill, for that softball. Well, myself and a group of 2 other colleagues have been working in various methods for uncertainty analysis, design, and basically understanding the impacts of uncertainty on robustness, mission success. We have developed tools that can, I guess, do this in a probabilistic setting reasonably well. We also can accommodate those classes of uncertainties that are not well defined by probability. That is, those events that we simply don't have a lot of data on. A lot of this mission falls into that latter category, where we simply are functioning in a very large, vacuous, lack of knowledge situation. So we have tools at our disposal that can accommodate that situation as well. The TRL, of course, of those tools is still relatively low. But we're always actively looking for funding to pursue that actually. So if you know anybody that's interested in hiring 3 talented probabilistic and uncertainty quantification guys, we are your men. But seriously, I think this problem is particularly ripe for applying uncertainty, because pretty much every talk we heard today talked about uncertainty in one form or another, filtering into this problem. And I think any serious approach to this problem is going to have uncertainty quantification methods hand in hand throughout the entire process of coming up with a solution. That's my 2 cents on the problem.
And I would like to add that we really need robust and adaptive controls to go with the uncertainties that exist. Right. And that can go hand in hand with uncertainty analysis and quantification to assure a high probability of success.
Yeah.
Yes.
I was wondering, for the asteroid redirect, did you look, and you mentioned you wouldn't put like thrusters directly on the asteroid because you think it might be disintegrating and fly apart or something. But if it really asteroid really would become a threat, would that be a mission scenario you consider? Just kind of put a little thruster on the asteroid to redirect its trajectory itself, like make a space vehicle out of the asteroid. You know what I mean?
Yeah. Are you?
I'm wondering if that was considered in the early stages of this mission, to use that approach.
So can I attempt to encapsulate your question there? Are we talking about essentially putting kind of like pods on the asteroid itself that can function as a GNC and propulsion, that can actually essentially build this asteroid into a mini spacecraft?
Yeah, like just outfit the asteroid with a thruster that wouldn't endanger the spacecraft which comes close to it, and just shoot on there. I understand there's challenges with finding the spin rate and the center of gravity of the asteroid, but just shoot a thruster on it, and it attaches there, maybe drills in, and then propels the asteroid away from
That's
Earth.
interesting, because when I first heard this problem, that was exactly my idea. If we could somehow attach some autonomous thing to this asteroid, either a net of pods essentially that would have sensors and actuators on them that would just encapsulate the thing and then form itself. You could do it in system ID. You could have special grappling hooks on it to make capture easier. Just, you know, the same.
So maybe my question goes to Dan. Is that something which was considered in the early stages, or?
Yeah. So
what's the problem
back
there?
Up a little bit in just a little bit of history. Back in 2011, 2012, we had a workshop out at Caltech at the KISS Institute for Space Studies, out at KISS, the Keck Institute for Space Studies, excuse me. That is when this first idea of using solar electric propulsion for redirecting an asteroid or a boulder from a large asteroid was discussed in the near past. There's been discussions all the way back since 1903 about redirecting asteroids. The SEP propulsion, the high efficiency, is really the key technology to doing this. Because if you start talking about distributed systems, if you start talking about hydrazine or chemical propulsion, you just can't do it. It's just not enough efficiency. Again, depending on how much mass you want to move around, and there's this goal at least of getting to this 500 ton, if not on this first mission, but eventually. Distributed systems have been talked about, and we actually had a workshop last fall where there were some ideas, but they still weren't well fleshed out. And this mission is kind of, it was a convergence of the SEP technology demonstration out of NASA Space Technology Mission Directorate, and basically giving that technology, which has been talked about, and I mean, I've looked at it for 25 years here at NASA for human missions, and we'd love to have a 50+ kilowatt, you know, even hundreds of kilowatt SEP system. So here was an asteroid mission that fit with that technology. So that's kind of how the concept came together. There are certainly different options, and we actually have a broad agency announcement out right now for some industry input, but they're really still along kind of the main threads that we're looking at for this mission.
I will say that in the Option A mission, which is where you're supposed to go out to a smaller, relatively, rock, capture it and bring it back, before Dan's study looking in depth at Option B, there was 2 other studies that NASA chartered, and I was on the alternate capture system team. And the first thing we did was brainstorm ways of doing the detumble operation. And in fact, one of the concepts we got from a guy at JSC was to put thruster pods, but that was to do the D-spin of that smaller rock, which should be not a whole lot different from a fuel sense than the spacecraft doing the detumbling. But that, I always liked that idea.
Yeah,
it was
it's
kind of
the
a
translation part.
You put the things on there and you do and back off and let it do the detumble, and then you just come up and grab it.
Right.
So this mission is past that stage. It's decided that either it's option A or option B, right? Or is there some discussion out there about
I think pretty much it has kind of settled on these 2 different approaches, again, mainly to minimize mission cost, progress some of the technologies that have extensibility to other NASA missions. But you know, the whole idea of what I thought you were talking about before about dispersion, of actually using the fact that it could be a rubble pile, there are some different innovative ways to do that. Now, whether or not that's a good planetary defense technique, that's, you know, an open issue, because you do have the atmosphere. If you can disperse the object into small enough and guarantee it, you can use the atmosphere to absorb that energy of an actual impactor. The unknown is, okay, do you just make a problem worse by making a few big objects versus one big object? So.
And maybe to make one maybe you have to keep it compact.
To keep it compact, yeah.
But you're right, it may be dangerous to actually blow it apart.
Yeah.
Okay, thank you. I guess we're approaching 4 o'clock. If there are no other questions, I think we can adjourn now. I want to thank our panel.
I have one quick question for Dan. Are there any target asteroids that are ferromagnetic?
Well, okay, so that's an interesting question, and actually they probably all have some ferrous properties. They're made out of nickel and iron. Every single asteroid has some. I can almost conclusively say that, because it was in the primal material that made up the solar system. And I have talked on a number of times about using magnetics as a mechanism, but there's always this question, well, how do you know its magnetic properties? And without the characterization, we don't know. But I think that's another, at least as a secondary capture approach, that you could have some sort of magnetic electromagnet or even fixed magnet to as a redundant aspect, or maybe to collect any fragments that come off. If there is dust, they could be attracted to that.
Or even a non-contacting system.
And yeah, that's originally how I envisioned it. But because you don't know, and you want to design for all the possibilities, that hasn't been looked at. But I still think it's something that could have some applicability, because now you don't have to contact, but you do have to worry about the effect of that magnetic field. Unintended consequences if you start to pick up regolith from the surface, just like iron filings when you try to pick up a steel ball. So that's another issue. But yes, they all have some amount of ferrous properties to them.
Yeah, if there's magnetic properties, you probably can measure that remotely. You may want to zero in on an asteroid that wasn't particularly magnetic.
Okay, great. Nope. Now it's great. Maybe. We're still not great. Now we're great. I just wanted to say thank you for you all for attending and sticking around for the panel discussion and taking a chance on this cross-directorate forum. I also do want to mention, if you have time and the presenters are still here, feel free to talk after this. We're just stopping filming and the main event at 4. So feel free to keep the conversation going, network after today and keep it moving with the ideas. If you have any ideas for future cross-directorate forums, please check out the cross-directorate forum site. It's https /sites@larc.nasa.gov, and you can search cross-directorate forum or CDF. And please remember to fill out the surveys that were on your seats. And I just want to, before we go, I want to take the time to thank each of our presenters and our facilitator. And we do have certificates for you all of our appreciation. So I did want to give one to Suresh, Dr. Suresh. Thank you. Everyone can clap. Thanks. We have one for Dr. Keith Belvin. We have one for Mr. Dan Maznek. Mr. John Dorsey. Dr. Carlos Rothmeyer and Dr. Haijun Shen. And I just wanted to say thank you again for taking the time. I think we had good discussions today. And our facilitator, Dr. Sean Kenny. So thank you again, and we're going to wrap up, but please feel free to take the time to talk with our presenters and keep the ideas going. So thanks, guys.